Papa SSGN Project 661. Our story begins on August 28, 1958, with a resolution of the Central Committee for the CPSU and the Council of Ministers for the USSR to create a new high-speed submarine and a new type of power plant to push the submarine through the water. Project 661 ANCAR is authorized, and TSKB-16, that's Submarine Design Bureau 16, now called Submarine Design Bureau Malachite, will design the new submarine. This is going to be a high-speed submarine that can launch a new anti-ship missile from a submerged position. And this is a new technology that they're testing. One, they want to push a submarine through the water as fast as possible. That's the first goal. The second goal is the missile boys over there in the missile factories have come up with this new anti-ship missile that can be launched from a submerged platform. Up to this point, all the anti-ship cruise missiles have been launched from submarines in a surfaced position. So the submarines need to expose themselves, which is not good for the survivability of the crew and the ship, and then launch their attack and then submerge again, which takes time as well. Well, with this new missile, they can launch from essentially periscope depth, which will add to the survivability of the submarine, and the effectiveness of the missile is improved due to the surprise factor of this attack. So they want to design a platform that can take advantage of this new missile. All right, Severnance Northern Machine Building Enterprise gets the orders to build the submarine. Technical design drawings are delivered in 1961, and they call for a titanium hull. The reason why they're using titanium is because it's lightweight, strong, low magnetic, anti-corrosion characteristics as well. Now the tools, right now there's no tools that exist to make this hull, so they need to create the tools to create the ship, and they begin doing that in 1961. And that's what shipyards do. Every time they get a new design, there's some form of setup process that they have to begin before they actually begin construction of the ship. So it's a year later, 1962, where the first hull sections begin to be produced in Severnensk. It is a two-hull design. Both hulls are titanium. So it's an outer hull encompassing an inner hull, that is the pressure hull. Both are titanium. So this is a very expensive, very difficult process, but it's overall very lightweight. The reason why they're using titanium for the most part is for the weight restrictions, because again, they're trying to get that high speed. And titanium is much lighter than steel. Steel would have been the other option. Okay, construction lasted almost 10 years because it's a very difficult process, and it's the first time they're doing an all-titanium hull. Commissioned finally in December 31st, 1969, just before the end of the decade, literally just before the end of the decade. They had two choices of reactors to go into the Papa SSGN. One was the simpler and proven water pressurized reactor that they had used before. And one was a new idea up and coming that they would eventually use on the Alpha submarine that used a lead bismuth cooled reactor, which is a liquid metal cooled reactor. It gives you an idea of how hot these reactors are, that they can actually use metal as a coolant, liquid metal. Well, they went with the water pressurized reactor because it was more practical, and they had the design already, and they could just, use a modified version of the current idea of the current pressurized water reactor. One of the nice things about this reactor is that it has a pipe-in-pipe system. So if you imagine two pipes, one very thin, is inside a much larger diameter pipe. The thin pipe is the primary loop. That's the pure water that actually touches the reactor core and gets very hot, but it's pressurized so it doesn't flash to steam. It just stays as a very hot liquid. That's why it's water pressurized reactor. And that goes through this very thin pipe through a fatter pipe that is the secondary loop. And that again is water, but it's not pressurized so that when it does get hot, it flashes to steam. And that steam is what turns all the generators and the main turbine that turns the shaft. That steam is what powers everything in the engine room. So it's a pipe-in-pipe system. The reason why the pipe-in-pipe system is so important is it allows for a very compact design. It doesn't take up as much space because you don't have two pipes running parallel to each other or in the vicinity of each other. One pipe is literally inside the other pipe, one just being a small pipe, one being a larger pipe. Now, because they put two reactors on this ship, two completely independent reactors, they didn't put a diesel generator, and this is a real first for a submarine. They don't need a diesel backup generator because they have 2 reactors. One reactor will be the backup for the other if either one goes down. Both reactors are identical and they're autonomous. In other words, they don't share any systems. So if there's a problem with one, if one scrams or is down for maintenance, the other one can still power the ship. And they still have a very strong battery as a backup source. In the unlikely event that they lose both reactors at the same time, they still have a battery to power emergency systems, get them to the surface, and radio for help. So a 2-reactor, no diesel engine, strong battery. One of the advantages of taking out the diesel generator is, one, it saves them a lot of weight. Diesel generator and all of its systems are very heavy, and the fuel oil that is just basically pushed around the ocean as they go on deployment and very rarely used, maybe only in an emergency, is a lot of weight as well. So while there is some additional weight, obviously, in adding a second reactor, but of course, they save themselves a lot of weight by taking out this diesel generator. All right, weapon systems. Let's talk about the Amethyst missile. Its NATO name, SSN-9 Sirene. It's an anti-ship cruise missile. They put 10 of them on the Papa SSGN. There's 5 on the port side, 5 on the starboard side, just forward of the sail. They are in individual tubes that are on a 32-degree incline facing forward, and they're between the pressure hull and the outer hull. Remember, we said this is a 2-hull submarine. So you got the inner hull, you got these missile tubes facing forward, kind of at a 32-degree angle, aiming kind of up a little bit. And then you have an outer hull around all of that. 2-hull submarine, 10 missile tubes on the outside. So the Amethyst uses a solid fuel rocket motor to launch up to about 200 meters in altitude. Pretty high altitude for compared to today's cruise missile standards. But for them, this is still pretty revolutionary that this thing is even coming out of the water at all. So it goes up to 200 meters in altitude where the rocket motor burns out, and it transitions to a turbofan propulsion, much like today's cruise missiles do. Whether it's the Tomahawk or the Harpoon, those use turbofan propulsion. Well, this one did too, but it did it back in the 60s. So it does have a nose radar that's used for target acquisition, and has also an infrared sensor on the top ventral wing as a backup for target detection, because they know as they close on the fleet or on the target, there's going to be electronic jamming. There's going to be ECM countermeasures to try and confuse and obscure the radar picture of the target in a hope that the missile will just miss the ship by enough to not damage it. So as a backup to that, during its terminal phase, it has an infrared seeker to assist the radar in case the radar begins to wash out. This is a great countermeasure to ECM. Okay, the launch depth is 30 meters, which that's a little bit deeper than periscope depth, but 30 meters is where they're going to launch it from. The cruise missile has a range of about 70 kilometers. It is a subsonic missile. It's about 0.9 Mach, so just below supersonic. Submerged launch depth is done in, submerged launch is done in 2 salvos of 5 each. And this is a real limitation that the designers did not like, but because the technology they had at the time with their fire control systems, they couldn't add enough data to the missiles to launch them all at once. So they had to launch them a maximum of 5 at a time. They couldn't do more than 5 at a time. So, and there was a 3-minute reset between each launch. And that's a real problem because you only get 1 surprise attack. You don't get 2 surprise attacks on the same target. So the choices were to shoot 5 missiles and run away, come back another day, or shoot 5 missiles, wait 3 minutes and hope you're not counterfired on or attacked, and shoot again 5 more missiles. And so that's a real tactical limitation, but it's the limitations they had at the time. There's 4 53-centimeter torpedo tubes in the bow, and those can be launched down to a depth of about 200 meters, so pretty deep. They have 12 torpedo stows in the torpedo room and the Lodaga fire control system. All right, sonar navigation and communication. Here you have the MGK 300 sonar, allowed for 2 simultaneous target tracks to go to fire control, which is pretty standard for the time. They had the Radion 1 mine detection sonar, which is a high-frequency forward-looking sonar. Sigma 661 navigation complex, allowed for under-ice operations, so she was Arctic capable, which makes sense because she was stationed out of the Northern Fleet, which is Kola Peninsula. They're on the western face, as they call it in Russia, towards the Atlantic. The automatic ship course and depth control was the Shapar system. And the Signal 661 General Ship Systems Control, that's like opening and operating all the valves for ballasting and other operations around the ship. That's all kind of done by that. And the MTP-10 surface radar, just a short-range surface and navigational radar. Okay, Papa SSGN by the numbers. 106 meters long and 11.5 meters beam, which means wide. Approximately 7,000 tons displacement. There's a little bit of a flexibility in that number. Multiple sources have different tonnages, but they're in the vicinity of 7,000 tons, which would make sense for the speed that it goes with the horsepower that it has. So the 7,000 tons is about right. There's a 400-meter test depth estimated. She does have 2 shafts of 5-bladed propellers. The propellers were shrouded at one time, and then they were not shrouded towards the end of her life, so it's possible that the shrouds were removed at some point, but initially she did have shrouds around the propeller. Okay, she had 2 B5 Papa water pressurized reactors. Again, they're both autonomous, completely turning their own main turbines, which is the big engine turbine that turns the shaft and the thrust bearing all the way down to the screw. Those are completely independent of each other. And each one of those produces 40,000 horsepower. Now, just to give you an idea of how much that is, the American Navy Seawolf-class submarine has 1 shaft that produces 45,000 horsepower. This one has 2 shafts in the 1960s that each produce 40,000 horsepower. It is an enormous amount of power and torque that is pushing the submarine through the water. And this is how they achieve such high speeds. It's relatively lightweight for as much as it has going on inside with like 2 reactors, which obviously is pretty heavy. But their power to weight ratio is so high, they're able to achieve 44.7 knots. Their officers to crew ratio is also kind of skewed a little. They have 25 officers to 55 crew. Now, typically on a submarine, you'll have 1 officer for every 8 to 10 enlisted men. In this case, they have about a 1-to-2 ratio of officers to crew. And that could be because of the high visibility this platform had. It was good for everyone's career, whether they were officer or enlisted, to serve well on the Papa SSGN. And she had approximately 80-day endurance, which is pretty good for the time. She could stay at sea for over almost 3 months. All right, let's talk about the one and only hull they made of this class. The K-162 was her original name. Eventually, she would be renamed K-222, which is what she's more popularly known as today. NATO designation Papa. The Russian Navy called her the Golden Fish. I've also seen this called Goldfish. So it's either golden or goldfish. Both apply in this case. The reason for this varies. 2 reasons. One of them are the titanium hull turned a golden color while during construction, and it kind of, before they had the paint and stuff on it, looked pretty golden, which is the less likely reason. The more likely reason is the sheer expense of this thing. This was an expensive submarine that took, a decade to build and used the most expensive materials and was just, a completely over budgeted project. And so that is the more likely reason it was called the Golden Fish by the Russian Navy crews. All right, in 1963, December 8th, the first keel section is laid in Workshop 42 in Severodvinsk. In 1965, January 27th, titanium welding is done in an airtight chamber with welders in diving suits using argon medium and tungsten electrodes. So right away, we're doing brand new construction techniques in a very unique airtight environment that is very dangerous and very expensive. And we haven't even got the construction done yet. So in 1969, after she's commissioned, during sea trials, she brings her reactors up to 80% power, and just at 80% achieves 42 knots for 12 hours. She transits for 12 hours, half a day at 42 knots. She travels an immense distance during this sea trial test, and everybody's really impressed. But during this test, she rips off 3 missile tube hatches, the sail access cover, and the emergency distress beacon buoy cover. are just completely ripped off. And what blows my mind is that after they lost the first missile tube hatch, they didn't stop. They kept going. I wonder if they would have ripped them all off eventually, probably. So in 1979, the next year, December 9th, she does join the Northern Fleet and becomes operational. A few days later, about a week later, in December 17th, and December 18th, a world record-setting test is scheduled with Admiral Maslov, chief designer Sholtenko, and construction contractor Palenko on board. And all three must agree to do this if they're going to try and bring the reactor up to 100%. Well, they agree to bring the reactor up to 97.7%, and they achieve a speed of 44.7 knots. There is immense vibration in the center line of the ship, and they don't go to a full 100%, but 97.7% is close enough for them, and they reach 44.7 knots submerged, sustained. The next year, in 1971, in October, she is deployed to the North Atlantic, where she does trail the USS Saratoga battle group across the Atlantic. Now, she is not quiet at all. The Americans know that she's there, but there's nothing they can do about it. The ship is so fast. Every time they send out, a submarine to chase her away, or some helicopter units to detect her and lay down sonar buoy fields, she can simply go around them. She's not worried about being counter-detected as much as she is being a pain in the American side with her abilities. All she has to do is stay within 70 kilometers to apply her trade to shoot her missiles. And so she trails the USS Saratoga across the Atlantic. In 1974, she does go to dry dock. She has post-dry dock testing afterwards, resulting in seawater leaking from sonar transducers into the submarine. So as the sonar transducers are mounted on the little cylinder in the bow, there is an area between the inside of the cylinder and the outside that has a gasket on it. Well, one of the gaskets started leaking and had some water go inside there. It caused real damage and problems, but nobody was hurt. It's more common than you would think, the sonar transducers leaking. Okay, 1975, took part in the Ocean 75 war games in the Atlantic. Those are Russian war games. And she was observed from a long distance away, obviously, because she's so loud. And we just observed her tactics and how she would conduct her attacks. And she was successful in those war games in conducting multiple attacks on Russian surface units. In 1978, January 15th, she's assigned the new number K-222. And that's what she's known as today. All right, K-222. In 1980, during post-dry dock testing, the reactor protection system failed. There's mechanical and electronic systems that keep the reactor from overpowering or doing something that would damage the reactor. Well, those protection systems failed, resulting in an increase in reactor temperature and pressure, which depressurized the primary loop. The problem with depressurizing the primary loop is, one, the only way that happens is if there's a leak, so there must have been a leak, and that primary loop that's under pressure flashes the steam. That's really bad because that steam has to go somewhere, which is probably the secondary loop, and it leaves the fuel exposed to air because that void that the steam leaves and fills becomes air. And without cooling on the reactor fuel, it will melt. It won't explode or anything like that, but it simply melts, and that causes a real problem when that happens. Well, thankfully, there were no injuries. They stopped the depressurization before any of that happened, and were able to get it all cleaned up. But there was a reactor incident on the K-222 during post-dry dock testing in 1980. Okay, 1981, she conducted a 3-month patrol in the North Atlantic. It was uneventful. We watched her from a distance, a large distance. She demonstrated that she's fast and she's looking for people, but because she's so noisy, we were able to kind of go around her. When I say we, I'm talking about the NATO fleets. Okay, in 1984, she is finally decommissioned, and in 1988, she's put into dry dock at Severnensk for disposal. It is over almost 20 years later, just over 20 years later, when in 2010, she's eventually cut apart. The reason for this delay is because the disposal of these nuclear submarines are very expensive. And we've seen this time and time again with just about every single decommissioning of a nuclear submarine, whether it's in the Royal Navy or it's in even the American Navy or the Russian Navy. These ships sit, in dry dock until there's enough means and people and time to dismantle them. And in this case, it took over 20 years before they finally cut her apart, and the reactor compartment is kept afloat for defueling. So even after they're done cutting her apart, as you see here, the reactor compartment is still intact. So it isn't until 2014 and 15 that they remove over 700 fuel rods from both reactors. It takes over a year to do that. And today, the Papa's reactor is sitting in storage, long-term storage in Saidye Bay, Kola Peninsula. And Saidye Bay is one of the long-term nuclear reactor storages for the Russian Navy. You can see a lot of reactors just basically stacked up side by side, Russian reactor compartments, all just kind of sitting there. And they're in shielded containers now, and they'll just sit there forever. All right, so my final thoughts on the Papa SSGN is what a time the 1950s and 60s were. I mean, they did amazing things between launching Sputnik to producing, submerged submarines that do almost 45 knots. It was just really an incredible time for both the Americans and the Russians. Both countries made a lot of achievements and improvements in these 2 decades, 50s and 60s. Papa SSGN demonstrates the capability of submarine nuclear power taken to the extreme, which means we're capable of doing these incredible designs and pushing our submarines faster and faster. The reality is we can't afford to do that and maintain that. That's why, even though we have this ability and this technology, both NATO and Russia, we don't build these anymore to this level because of the cost it takes to maintain this fleet. So the Papa really was a demonstration in fiscal irresponsibility, and the feasibility of this program was ended after this one hull was built, just due to the cost of it. On the other hand, had they been able to afford even a squadron of these, much less a fleet, they would have done, it would have changed the Cold War, because this submarine was able to trail American carrier groups across the Atlantic, and they would have been able to do in the Pacific if they had some over there. There wouldn't have been any reason why they wouldn't. So thank goodness they couldn't afford to build more. So it was very ahead of its time. It had a high kill probability because of the surprise attack nature of its missile attack, even though it was limited to only 5 missiles per launch per salvo with a 3-minute period in between, and that is a severe tactical liability again. That initial surprise attack would probably get a ship or two. The Papa was very noisy, which was a problem for her, but the Americans didn't really have a counter to her, even though we could hear her coming a mile away. She was so fast by the time we got over to her and was dropping sonar buoys on her from airplanes and helicopters. She was simply moving out of the field, out of the sonar buoy field. We could keep up, we could track her with our submarines, but we could not keep up with her. So we could watch her run away for miles and miles, but we couldn't keep up with her. We'd have to hand her off to another unit. So she was very tactically impressive. And a fleet, like I said, of Papa SSGNs would have changed the nature of the Cold War. I stand by that statement. Thank goodness they didn't build more. All right. And that is Papa SSGN Project 661. Thanks for listening, everybody. This has been written and read by Aaron Amick.